this video, I hope to address two issues. The first issue is this one. Alright, why is this so often used? Why is this so important? Okay, and the next one is actually the Nyquist stability criterion. Okay, where if there is one z, alright, 1 0, meaning this one, in the right half plane Nyquist contour. Nyquist contour is simply this type of contour. Alright, this is this whole thing. Alright, this whole thing is in fact the Nyquist contour. Alright, if there is 1 0, meaning if there is just 1 0, alright, it's just 1 0 over here, this means the whole equation is unstable. Alright, or the whole transfer function is unstable. So we're gonna show you this two in this video. So I hope that is pretty cool. And therefore, start off with a question. Alright, we have an open loop G and an open loop H system. Alright, the open loop defines like this: G, H. Alright, it's just open loop. And after, when we plot, alright, this now we're gonna plot this. We're gonna check whether is the system stable, right? Whether is this system by itself stable. So when we do out the roots, because there is no zeros over here, right? They are all numbers, but we have poles. So the poles for the G system is actually this two. Okay, is this two. And the poles for this H system is over here. As you can see, there is no poles or zeros in the right half plane. There is no, meaning no. Okay, this means that there is this two system is stable. Alright, our starting system is stable. So given that our starting system is stable, alright, this is our first step, alright, to become stable. Okay, what I mean is, if your system initially, when you start, is not stable, then definitely at the end of the day, it becomes not stable, right? So when you start, if it's stable, and then if you close the loop now, alright, now I close G and H, then if it's unstable, then at least we know that maybe we can add in something to make it stable, right? Because if this by itself is already unstable, if you run a system, definitely it will also be unstable. That's the logic behind that, okay? And therefore, in order to do that now, to see whether is it unstable, we will mix G and H together in a closed loop system like that. Alright, so if you were to remember, this one is the forward loop. Alright, this is the closed loop transfer function actually. So the forward loop G divided by the feedback loop of 1 plus GH, correct? And then when we sub in G, alright, the G is simply the equation over here. Okay, I'm just simply subbing in all this equation if you don't know what I mean. So G and H are all sub in over here. Right, G is over here also. So I'll just sub in all the equations, meaning I think you get what I mean already, okay? So therefore, when I sub in the equations, I rearrange and eventually I'll get this equation over here. Alright, once I get this equation over here, this is in fact our system response. Alright, so if I were to take this system response, alright, I'll just plot it in the contour. Alright, this is the this contour previously, alright, that I plot for the 2 poles and 1 pole over here, this one is for the open loop Nyquist contour. Alright, now using this response, I'm gonna plot this one into here. Alright, and I can visualize how many poles and zeros in that is actually causing troubles in the right half plane, right? Because we say that we want to know how many poles and zeros, and therefore I can know that there is 1 0. Alright, because if you factorize out, I have 250 as plus 2, right? So 1 0 is over here. Alright, and then I have 3 poles. Alright, because I solve for the roots over here, set it equals to 0, and then I just find the roots. I have 2 poles over here and 1 pole over here. Alright, as you can see, this 3 poles actually translated their position. Initially they were here, right? So after you run the response, they actually move over here, you see? Which is shown in this picture right here, right? They actually moved, their position moved. And in addition, there is 1 more 0 over here. By any of the case, there is 2 poles in the system, and therefore it's unstable. And we can solve for things already, right? We can be very happy, right? Oh, how does this come in? what is the importance of this equation? The importance of this equation comes in when you're talking about more than two system, or maybe 3 system or 4 system, or talking about 1000 system. If you have 1000 system, then how the hell are you going to plot? Right, you can't plot the whole map over here, right? You can't plot, you just plot everything. There's so many zero. How can you count? You cannot count, right? Instead of plotting, we can solve for the numerator and solve for the denominator also, right? So when we solve for a huge chunk of like maybe s10 plus, example, if I have a closed loop transfer function right here, okay, if I want to solve, I can actually solve for this numerator and then the denominator, alright, and then eventually I find the roots already, right? For example, if it has the roots of something like that, okay, if I were to find the roots and then I rearrange in terms of the system, for example, this is totally unrelated, but for example, if they're equals, alright, we can see that there is zeros, alright, there's zeros that is inside the right half plane, because what makes this thing 0 is actually, for example, s minus 5. What makes this thing is equals to 0 is when s is 5. So if you have 5 over here, this means that my 0 is over here. This means it's inside the right half plane. That's what I mean. And therefore, if I solve already, I know that there is this thing, and then I can calculate for I can calculate which equation has a plane, alright, by the terms over here. If it's negative, then this means that it is within the system. If it's positive, like this one, then it is within the system. So I can use computer system to actually sort it out, right? Now the shortcoming is that you actually waste data. Why do I waste data? Is because you have to compute for the 0 and you have to compute for the poles, which is very inefficient, right? You're gonna compute two things all together. Therefore, Nyquist plot, alright, offer a better alternative that you can actually solve for the denominator will do. Alright, this actually save out a lot of space. Alright, if you use Nyquist, then this equation is gonna comes in. Right, what I mean is if you use Nyquist plot lah. Alright, this one, alright, don't be confused, is that this contour is Nyquist contour. Okay, this contour is Nyquist contour, and then this one is the Nyquist plot, the thing that we're always talking about. So we just plot each of the point, right? We plot each of the point, we map over here, we map over here. So we are just mapping, alright? We can also map this point, we map this point, we just simply map all of the point. Alright, it should be mapping all over here, alright, along this contour. Alright. So we're actually mapping this contour, this Nyquist contour, into this Nyquist plot. This is just how the Nyquist plot is being born, right? Therefore, when you see the reason behind this, alright, then how do we utilize the Nyquist plot then? And therefore, let's talk about the encirclement. If you remember the encirclement in our case is going in the anti-clockwise direction. You see, it's going in the anti-clockwise direction. Alright, and as you can see, it encircle this point is the -1 point. Alright, it encircle one time. Right, if this is like that, it's encircle one time. Encircle one time, meaning if you were to like that, right? But if you go here, encircle one time already, and then you go in again, and then you encircle one time more, then you can encircle 2 times. Right? So this is in terms of calculating the encirclement. Alright, in terms of clockwise or anti-clockwise. And if you take a look in this definition, n is the number of clockwise on the -1 in the Nyquist plot. So as you can see, it's clockwise. This means if there is one clockwise encirclement, alright, for example, if -1 is over here, if you encircle one time, alright, something like that, okay, if you encircle it one time, then n is equals to 1 in the clockwise direction. If it's encircling in the anti-clockwise direction, then n is equals to -1. Alright, so the clockwise is a very important piece of information. So clockwise, n is equals to 1. If it's anti-clockwise, n is equals to minus 1. If given that there is only one encirclement, if it's, for example, 2 encirclement, alright, it's going 2 times, then n is equals to 2 lah, if it's clockwise and things like that. I hope this is pretty clear. In our examples over here, right, this is the example that we started on from these two systems, right? We actually solve the closed loop system, and then we have a response, and then therefore we use this response, we plot the Nyquist plot, and we have the Nyquist plot over here, and then from here we would know that there is one encirclement in the anti-clockwise, and then the second encirclement in the anti-clockwise also, and therefore we can say that n is equals to, right, minus 2. Next, since we know, okay, maybe I should clear things up a little bit. Come here, okay. So since we know that this is the closed loop transfer function, and we are keen to know what is the closed loop poles now, because we say that since we know the Nyquist, alright, therefore we can just find the number of poles that is in the right half plane. Then we can use this formula, alright, this formula to find the number of zeros without actually calculating for both zeros and poles in the closed loop system, right? So this actually saves a lot of space. And if you remember, the closed loop system is g over 1 plus gh, correct? This thing, if you take a look, is 1 plus gh is equals to 0. This thing is the characteristic equation, right? Which is very familiar to you, right? It also contains the full information of your system, right? It contains the full information, including the forward loop and the feedback loop, everything, right? It contains all of the information within this system, and therefore this is also another reason why we only choose the pole, right? Because this one contains the full information on everything, right? If you have like a big chunk of information, for example like that, right? You have a big huge chunk. For the forward loop is only KLM, that's all, right? But for the feedback loop is KLM, QPR, QP, OPQ, right? It's going all the way in this whole loop. So this closed loop poles actually contain a lot of information compared to this one, alright? And therefore, containing this information is good, is because we can straight away get the input, alright? You can straight away get the input. The input is given already, ma. Right, these are the input G and H, right? Open loop G and H. So you can just straight away sub it in, and then we can find the roots and things like that, which is much more easier, correct? So solving for this characteristic equation for our example, I'll have 3 poles, right? One at minus 7.5, alright, and 2 conjugate poles at plus 1.12 plus minus 8i. So as you can see, if you were to still remember back our contour, the minus 7.5 pole is actually over here, and the 2 conjugate pole of 1.12 plus minus 8 point something I, alright, is over here, right? It's just these two poles. And then from here we know that there is 2 poles, or can straight away no need to see this one, because you can also straight away know from your result calculation that there is a 1 positive rail, right? Perhaps 1 pair of conjugate rail, alright, in real number in the system, and therefore the rail I mean is this one in the real axis. Real axis positive is 1, 2, 3, and therefore it's within this right half plane. Alright, so there is 2. We know that there is 2 poles, as can be seen here, and also been calculated also. And therefore we have 2 over here, right, plus 2, and therefore this is from the Nyquist plot, this is from our 1 plus GH characteristic equation. Then we can know that the number of zeros in the right half plane is 0, and it can be reflected over here. There is no 0 over here, right? There is no 0, it's only 1 0 in the left half plane. So from here then we can know that there is no 0 in the right half plane, alright? So the 0 z over here is to define the number of 0 in the right half plane, while the p is to define the number of pole in the right half plane. So remember, it's in the right half plane, okay? It's not in the contour, alright? So therefore this is the behind why this thing, alright, this thing is so useful, okay? But if you, so just to, because didn't actually specify to you much on the method to solve. Alright, if you are given two closed loop transfer function, or you have more than two or maybe other stuff closed loop transfer function, the first thing first you do is to solve for its closed loop transfer function. The first thing first is to solve for the closed loop transfer function. Next, once you get the transfer function already, alright, you plot it into the Nyquist plot, which is over here. And then you calculate the number of encirclement, clockwise or anti-clockwise. Then you will know that it's the number for n. Right, this is the first step. The second step deals with the response also. We have this is the response, right? We can use it to plot the Nyquist plot. While we take the denominator response, we solve for its roots, alright, which is this thing in our case, and we just calculate what are the number of positive real, alright, number of positive real numbers. If there is in our case it's 2 positive because it's conjugate, right? Then we can say that P is 2. This is why it's over here. So this is the second step. So first step is to find the, where do I record? But anyway, I just repeat again, okay? So the first step first is to find the system closed loop transfer function and plot the Nyquist. Alright? And then using the same closed loop transfer function, you find its denominator or the characteristic equation to solve the roots, that is, to find the number of poles in the right half plane by determining how many positive real values. Alright, if you don't know why I'm talking, you just click back a few seconds ago or a few minutes ago, you understand what I mean. And then the last step is to just, since you know n and p value, and then you will just solve for z. Alright, so if z, this is the Nyquist stability criterion already, if z is more than 0, then it's unstable. So this means that if there is any one of the zeros in the right half plane, this is considered unstable. Alright, and therefore in this part, alright, in this quicker part right now, I'm going to share with you why it's only z. Alright, why do we say that if any z is in the right half plane, alright, more than 0, is considered unstable, while if we can actually tolerate the number of poles over here. We can tolerate the number of poles for the closed loop only. Alright, please remember that we can only tolerate the number of poles in the right half plane applied for only the closed loop. Right, for only the closed loop. Okay, please. Okay, my fault, sorry, my fault. Don't take back my words, okay? It's not for the closed loop, it's for the open loop. Alright, we can tolerate the number of poles in the right half plane for open loop. In this case, the open loop are this two, right? If you remember this two equation. If this is like minus, then we can tolerate it. Because after doing the closed loop transfer function, alright, it may actually move the poles into this side. Alright, it may actually move the poles into this side. And therefore, then the closed loop is actually, the closed loop response is actually stable. But we cannot tolerate, alright, we can't tolerate the number of poles in the right half plane for closed loop. And therefore, this is why I say that this thing is considered unstable, because this is the closed loop contour. Alright, as you can see from our poles also, that there is a positive real for the poles value. Therefore, it's unstable also. So please remember these definitions, okay? Please remember my I don't know what the hell am I talking just now. But anyway, this is two important understanding you need to know. We can tolerate the number of poles in the right half plane as long as z is equals to 0. Okay, as long as z is equals to 0. For example, if you take a look, this, for example, okay, this is another example, alright? We have open loop L. Okay, the open loop L is this transfer function. Okay, when we expand, we see that there is a negative over here. Alright, this is the open loop poles. As you can see, the open loop, one of the open loop poles is over here. Alright, and the open loop zeros is s plus 3, which is shown over here. And then the other poles is over here. Alright, so we can still say that this is stable. Alright, this poles in the open loop is stable. If there is 0 over here, then no, then it's definitely unstable. Alright, this is only for open loop. Now, after we run a closed loop system, meaning we put this as L of S, and then we run a closed loop system like that. Alright, if we close the loop, what do we have? Example can also help you to apply this learning concept that we have learned. Alright, so let's do it. Alright, so if we close the loop and plot the Nyquist plot, alright, the Nyquist plot is this one. And why do you need the Nyquist plot? Because you want to determine the number of n, right? The number of encirclement, clockwise encirclement. And therefore, if you take a look at this Nyquist plot, it's going in the anti-clockwise again. Alright, the negative one is over here. So it encircled this one time, right? Because it's encircled the minus 1 in this manner. In other words, this minus 1 point is inside the loop over here. So therefore, since this is anti-clockwise, so therefore n is equals to minus 1. Alright, the next step what we do is to take the characteristic equation of the closed loop transfer function. Right, this is what we say. And then we find the number of poles in the right half plane. So therefore, if we were to solve for the characteristic equation, this is simply 1 plus GH equals to 0, right? And 1 plus GH, or in other words, in our case, is only L. The L of S is equals to this one or this one. So you just simply 1 plus LS is equals to 0. And then we solve for the roots. And this is why the method is over here. L of S is this. 1 plus L of S is this. I solve, eventually I have this over here. I rearrange, I have this. Okay, and when I have this, you see, these are all positive. Alright, so this means that if you were to solve for the roots itself, minus I plus, we have minus 5 plus minus I. Okay, or in other words, if you want to visualize things, the two poles that we have found, alright, is actually over here. So therefore, in this spot over here, alright, this pole actually moved, or perhaps this, and also perhaps this poles also move. Alright, so they actually move from each of this side to this side. So as you can see in the closed, this system right here is for the open loop. Just now we say, right? After we close the loop, alright, the poles is gone. Alright, the poles is gone, and it actually moved to this portion over here. Alright, and I don't know whether it's the 0, because we are only concerned of whether are there any zeros over here. So we actually don't care about whether the 0 position, whether is it here. As long as it's within here now, then it's not unstable. And how can we determine that? Alright, since we know that there is two poles that, or in other words, there is no poles in the right half plane. Right, since there is no poles in the right half plane, then we can say that P is equals to 0. Right, this is P is equals to 0. We know that n is equals to minus 1, correct? Anti-clockwise, let's encircle the minus 1 point. Alright, and we know that P is, there is no poles in the right half plane, so P is equals to 0. Right, and therefore we have with this, so P is equals to n plus P, right? So minus 1 plus 0 equals to Z. And therefore, since in this case, we know that for the criteria, that Z must be, if it's more than 0, is unstable. And therefore from our finding, we know that Z is actually lesser than minus 1, and therefore this is stable. And we also shown you that actually there is there is no zeros, no poles over here. Or in other words, what I'm talking. In other words, at first I found my n, alright, and then I found my p, and then from here I can straight away know that how many zeros are there in the right half plane from this calculation. So in this example, we have shown you the application of using this equation, and also the stability criterion of how is it being able to help us determine the stability of a system. Alright, and therefore I think this is it, and yeah.